Welcome to the JBC English Learning Academy. We're here to take your curiosity, mix it with some really rich source material you've provided, and basically give you a conversational shortcut to getting deeply informed. Okay, let's unpack this. What you've given us here is just an incredible set of resources really focused on the sophisticated vocabulary and the core facts of space science. Today we're tackling, well, the lexicon of the cosmos. Essentially, it covers the whole spectrum, doesn't it? From, engineering right here on Earth, human ambition, all the way out to the invisible stuff, the fundamental forces shaping galaxies billions of years ago, light years away. And what really strikes me about this collection is just how interconnected everything is. You might think, okay, space exploration, that's government. Missions over here, theoretical physics, way over there, right? Separate boxes. Exactly. But what we see today, and what these sources really highlight, is the absolute synergy. I mean the detailed engineering that lets us, say, launch a rocket that's fundamentally tied to the cosmological theories we're trying to test by looking at light that's traveled for eons. That's a great point. So our mission today is to explore these 22 advanced concepts. We want to find the most surprising bits, really dig into the details from the material, and understand not just what these terms mean, but why they matter. Yes, why they fundamentally redefine our place in the universe. We need to get deep into the mechanisms, the implications, the history behind them. And well, to start that journey, I think we have to begin right here on Earth, with the institutions, the people, and frankly, the brutal physics that make any of this possible. Okay, so if we're talking cosmic ambition, the place to start has to be the institutional engine, right? For decades, it's been NASA, the National Aeronautics and Space Administration. Now, formally, it's the U.S. government Agency for Space Exploration and Aeronautics Research. But I mean, its actual role, its impact goes so much further than that definition. I completely agree. That simple description, it barely scratches the surface of its, well, its cultural weight, its technological footprint, its scientific gravity. You could say NASA isn't just paperwork. It's a proving ground for the most extreme engineering, the most groundbreaking science. Absolutely. And if you look at the examples in our material, you see that dual nature perfectly. You really do. On the science side, take the Perseverance rover on Mars. Just phenomenal success. It's actively driving around Jezero crater right now, an ancient lake bed, they think, right? And the key thing, as the sources emphasize, it's not just taking pictures. It's drilling, uncovering, sealing rock samples that strongly suggest, or at least hint at, the possibility of ancient microbial life having existed beyond Earth. Wow. That mission is pure foundational science. It's driving planetary discoveries, trying to answer that age-old question, are we alone? And then flip the coin. Look at the engineering side, the sheer, almost unbelievable complexity needed for something like the James Webb Space Telescope, JWST. Oh, absolutely. That observatory. It's sending back images of the universe's infancy, stuff we've never seen. But just getting it there, engineers had to design this massive folding mirror system What was it? 18 separate, hexagonal pieces. That's right, 18 segments. And they had to unfold perfectly, automatically millions of miles from Earth, sitting at a stable, rangy point. Just that feat alone deploying a tennis court-sized mirror with micron precision. In the vacuum of space, it speaks volumes about the level of engineering we're talking about. It really does. And it connects NASA directly back to that idea of aspiration you mentioned. It's the place where visionaries take things that sound like science fiction and somehow make them real, operational. So moving from the government agency itself to the industrial muscle behind it.
Yeah.
We get to aerospace, the sector defined as basically producing or operating aircraft or spacecraft.
And
its influence is often kind of overlooked, isn't it? We focus on the missions, the astronauts, the discoveries, but the economic effects, the technological spin-offs, they're huge.
Yeah.
And pervasive. Yeah, absolutely. The sources trace this massive boom in aerospace back to the post-Apollo era, right after the moon landing push.
Correct.
That huge injection of public money focused on this incredibly ambitious national goal didn't just build rockets. It spawned innovations in fundamental material science. And this is where the deep dive part is
key.
We're not just talking, cool rocket parts. We're talking about specialized thermal materials that ended up in ovens, insulation, right? Advanced composite structures making planes lighter, safer, miniaturization. Techniques that really drove early electronics. The sheer demand of space. Travel needing high-performance zero-failure components. It fundamentally changed how things were made back on
Earth.
And for anyone listening who's maybe thinking about careers, the sources really stress how interdisciplinary aerospace is.
Yeah.
It pulls together high-level physics, maths, but also creative problem-solving, engineering, design. It covers everything. It really does. From, say, advanced drone design, which needs totally new approaches, to aerodynamics, computational fluid dynamics, all the way to complex satellite deployment, logistics that needs massive computing power, incredibly detailed planning for orbital mechanics. And we have to touch on the dual nature of the sector as well. The sources are pretty clear that aerospace isn't just civilian exploration and science. No, not at all. It fundamentally includes military and defense applications, like the very current, very rapidly advancing field of hypersonic missile technology. That dual-use aspect is a crucial takeaway here. The same fluid dynamics, the same material science, the same
guidance systems you might use to send a
probe to Jupiter. They get adapted to develop systems flying at Mach 5, Mach 10, or even higher. So it really underscores how fundamental this sector is, both for expanding knowledge and, well, for global security.
Today.
2. The human and commercial element, manned flight and logistics. Okay, so we've got the institutions, the industry. Now let's bring in the ultimate variable, the human factor.
We
need to talk about manned spaceflight. Simply put, space travel with a human crew. And the history here, the geopolitical context, is just essential to understanding it. Oh, absolutely. Historically, the anchor point, the event that kicked it all off, is undeniably Yuri Gagarin's 1961 orbit. That wasn't just putting a person in
space. No.
It truly ignited the Cold War space race. It defined a whole decade of global competition, all centered on showing human capability, national technological strength. But the sources also flag a really profound modern shift, something changing the whole game. The implications of the first crewed space flight done by a private, non-governmental company. Yes, that's a huge marker. That milestone wasn't just another successful flight. It signals this new, evolving era. Commercial space, tourism, privatization. It changes the whole dynamic of who goes to space and why. It opens the door for non-government explorers, different objectives entirely. Yet even with all this technological progress, the basic human challenges, they're still immense. The sources really go into the rigorous psychological training astronauts need. That must be intense. Think about the isolation. Being confined in a tiny hostile metal can for months, maybe years. No quick way home. No immediate rescue possible if something goes wrong.
Yeah.
Getting to orbit is only half the battle. Staying mentally resilient, keeping the team working together, managing emotions in that kind of confined, high-stakes environment. Yeah, arguably that's the harder challenge for those long trips, which leads us straight into the physical demands. They're just inseparable from the physics of getting off this planet. Let's talk acceleration. Defined broadly as an increase in how fast something happens, or technically a change in velocity. But in a rocket launch context, that physical sensation is overwhelming, potentially dangerous. It's that moment where sheer physical force measured in G's, units of gravity, pins the astronauts deep into their
seats.
The sources explain that during a launch, the acceleration isn't constant. It's carefully managed. But those forces
aren't just about getting fast.
They're about the rapid change in velocity needed to beat Earth's gravity, hit escape velocity. It pushes the human body right to its limits. And it's fascinating how we've learned to deal with that force. Early rockets, they put astronauts through peak G loads that needed special seats, body positioning, restraints just to avoid blacking out or getting injured.
Yeah.
Snorts, the physical feeling is supposed to be like having several times your own body weight just crushing down
on your chest. Wow.
But connecting this to the bigger picture, the term itself, acceleration, it's so versatile. We use it literally for the physics of launch.
Sure. But the
sources remind us we use it metaphorically all the time to talk about the pace of change. That's true. We talk about the acceleration of polar ice melt because of climate change, or technologically the acceleration in AI development. AI that's now being used, interestingly, to simulate complex cosmic events. So it's a term that really goes beyond rocket science, defining rapid change everywhere. Okay? So we've launched, we survived the G-forces. Now we're looking back maybe at our local cosmic neighborhood.
So
let's shift focus. Observable geometry, orbital dynamics, and the really unique, sometimes counterintuitive physics of this near-Earth inner solar system.
Space.
1. Celestial mechanics and observation. Let's start with something ancient but still totally essential. A constellation, defined as a group of stars forming a recognizable shape in the sky. The history is just beautiful here, isn't it? Constellations are where deep human mythology bumps right up against hard science. For thousands of years, ancient cultures looked up connected those random dots of light into figures. Orion the hunter, Hercules the hero, the Plet sisters. These weren't just random patterns. They held stories, myths of gods and heroes. They created structure from the well, the cosmic chaos. But the sources really underscore their critical, practical, scientific role. Today, they're way more than just old stories. Astronomers use the 88 official constellations recognized by the International Astronomical Union as vital reference points for celestial
Crafty.
like cosmic addresses.
Exactly.
Think of them as the fixed grid system for the entire night sky.
They
Let astronomers accurately locate things, track them, communicate about objects no matter where you are on Earth. Observing from. Speaking of tracking and celestial geometry, that brings us to the really dramatic alignments. A solar or lunar eclipse. The sources define both.
clearly. Solar is when the moon blocks
The sun. Lunar is when the Earth's shadow falls on the moon. And the visual drama of a total solar eclipse. It's supposed to be unparalleled. Our material talks about that awe-inspiring moment where the moon's relatively tiny silhouette manages to perfectly cover the sun's main disk, right? Revealing the corona,
Yes.
that ghostly, wispy outer atmosphere of the sun. The corona, which you normally can't see at all because the sun's just too bright. That perfect alignment. It requires incredibly precise orbital mechanics, a cosmic coincidence almost. And the lunar side, the lunar eclipse is visually striking too, though much safer to watch directly. When Earth casts its shadow on the moon, you get that weird atmospheric effect, the reddish color, the blood moon, and the mechanism behind that blood moon color is quite neat. Worth unpacking a
Bit.
Earth's shadow isn't perfectly black because sunlight filters through the ring of our atmosphere all around the edge. Right. Our atmosphere scatters away the blue
Light.
That's why our sky looks blue. But the longer red wavelengths they get refracted or bent inwards by the atmosphere, and they land on the moon's surface within the shadow. So, it's like projecting sunsets onto the moon. Essentially, yes, it's like all the world's sunrises and sunsets being projected onto the moon at the same
Time.
But critically, the sources really hammer home the safety aspect for the solar eclipse. You absolutely need proper eye protection. Don't just stare at it. Definitely not. Viewing a solar eclipse, even a partial one, without certified filters, can cause permanent retinal damage. It's a powerful reminder. Observing the cosmos, even close by, demands caution. 2. Interplanetary travel and objects. Okay, moving beyond just watching from Earth or near orbit, let's think about truly vast distances. Sustained travel. The phrase to launch out on a long voyage.
It really speaks
To those big, long-duration expeditions. True exploration beyond our immediate gravitational neighborhood. That immediately makes me think of the unmanned pioneers. Their sheer longevity is just a testament to incredible engineering.
We're talking about the
Epic scale of the Voyager Pro, Voyager 1 and 2. Yeah, launched way back in 1977.
and our
Sources confirm they're still going, still talking to us, and are now actually wandering through the interstellar medium, the space between the stars, humanity's farthest emissaries. It's incredible. And the sources draw a nice parallel, noting how that phrase, launching out on a long voyage, echoes extreme terrestrial expeditions like crossing Antarctica or exploring deep sea trenches, right?
same vibe. Exactly.
In all cases, it signifies immense planning, needing to be totally self-sufficient, huge commitment, and just venturing into these distant, demanding, utterly unforgiving places. Okay, let's bring the focus back closer, but still out there. Threats and resources. The common space rock, the asteroid, snorts, defined simply as one of many large, irregular rocks orbiting the Sun, mostly in the main belt between Mars and Jupiter. But they're much more than just debris. Oh, definitely. They're central now to the whole concept of planetary defense. The sources mention NASA's proactive approach, specifically highlighting the DART mission, the double asteroid redirection test.
Right.
DART was fascinating. It really was. DART was what they call a kinetic impactor. It successfully showed we have the technology to actually change an asteroid's path in space. And let's flesh out DART a bit, because the idea wasn't like Hollywood style, blowing it up, right? No, not at all. It was about a subtle, long-term orbital shift. The spacecraft basically just rammed into a small, moonlit asteroid Timorphos at very high
speed.
A nudge. A cosmic nudge.
Exactly.
It proved that even a relatively small impact, if you apply it early enough, can significantly change the orbital period of a potentially hazardous object. A major step in, protecting Earth proactively. And then there's the other side, the opportunity, the economic potential. There's growing talk noted in our material about mining asteroids for rare metals.
Yeah.
Platinum group metals, nickel, iron, things valuable on Earth. This whole idea fuels a potential new era of space-based economies, maybe reducing reliance on digging everything out of our own planet. Still futuristic, but the potential is there, and we can't forget the historical impact these things have had. The sources remind us of the big one, the Chicxulub asteroid. Impact 66 million years ago. The dinosaur killer. Exactly. Triggered the mass extinction. So, these space rocks aren't just hazards or resources. They're genuinely planet-shaping, life-altering forces in the grand scheme of things. And all this planning, engineering, risk management. Yeah, it all feeds into the broader idea of space voyages defined simply as journeys outside Earth's atmosphere. If we look ahead, what do future logistics look like? Say for a trip to Mars. The focus there seems to be heavily on sustainability for long trips. Future Mars voyages won't be quick hops. They'll need highly sustainable closed-loop life support systems that can function for years. Right? Recycling everything. Everything. Air, water, plus things like Institute Resource Utilization or ISRU. Using local Martian resources, maybe. Water, ice, minerals to make fuel. Building materials, whatever's needed on site. Of course, there's always the visionary optimism angle we see mentioned. People who foresee space voyages becoming, no routine commutes, almost shrinking the solar system into a neighborhood. Like catching the orbital shuttle. Kind yet an optimistic view. Envisioning orbital trips, lunar visits, becoming standard fare. But the sources give a crucial reality check here, which we shouldn't ignore. They critique how media often romanticizes space, glossing over the harsh realities like the huge radiation hazards on long journeys. Once you're outside Earth's protective magnetic bubble, you're exposed constantly to solar flares, galactic, cosmic rays, particles that can damage DNA. The void is beautiful, immense. Sure, but it's fundamentally hostile to our biology. That's a major hurdle for long space voyages. 3. Physics in orbit. That hostile environment, particularly inside a spacecraft in orbit, brings us to the really weird physics of being there. Let's tackle weightless condition and zero gravity together. The state of having no apparent weight or where gravity seems to have no effect. And it's important, especially for a knowledgeable audience, to maybe clarify the terms a bit. Zero gravity is the common phrase, but scientifically what you experience in orbit is more accurately microgravity, or even better, continuous freefall. Right. Gravity is definitely still there. The International Space Station, for example, still experiences about 90% of Earth's surface gravity. Exactly. The feeling of weightlessness comes because the station and everything inside it is constantly falling around the Earth. It's not being held up. It's in a perpetual state of falling sideways, fast enough to miss the ground. And physiologically, that constant free fall forces astronauts into those tough exercise routines, right? Like 2 hours a day, absolutely necessary to fight off the bone density loss and muscle atrophy that happens when your body doesn't have to constantly work against gravity. And the changes are widespread, aren't they? The sources mention fluid shift because there's no down. Fluids redistribute upwards into the chest and head. Yeah, leading to that puffy face look, thinner legs, and potentially even affecting astronauts' vision over longer missions still being studied. But the physics itself leads to some cool, if quirky, effects like liquids forming perfect spheres in microgravity. Right? Totally defying our everyday experience of how water behaves under gravity. When you remove that dominant force, surface tension takes over and pulls the liquid into the most energy-efficient shape, a sphere. And this environment isn't just a novelty act. It has real scientific uses beyond just studying human bodies. The sources mention experiments on the ISS, yielding breakthroughs, specifically crystal growth for pharmaceuticals. Yes, without gravity causing sediments to settle or convection currents to stir things up, scientists can grow much larger, much more perfect crystals of proteins and other complex molecules, which helps them figure out the structure. Precisely. Better structural analysis can lead to understanding how diseases work at a molecular level and potentially designing new, more effective drugs. So, microgravity is a unique lab environment, and we can mimic this briefly back on Earth. We can using parabolic flights, often nicknamed the vomit comet for reasons You can probably guess. Oh, right. These planes fly in steep up and down arcs. During the downward arc, they basically achieve free fall for about 20-30 seconds, creating that zero weight sensation. It's used heavily for astronaut training, testing equipment, and sometimes even for adventure tourism. A brief taste of being weightless. Okay, we've left Earth, navigated the local physics. Now let's push out further into the core scientific field, searching for life and into the really strange, fascinating edges of reality that define deep space exploration. 1. Disciplines defining the cosmos. The foundation here has to be astronomy, defined simply as the scientific study of everything beyond our atmosphere. Sun, moon, stars, planets, galaxies, the whole lot. It's the observational science that maps and measures the universe. And the insights it provides are just humbling. Astronomy by measuring the universe's expansion rate, looking at the oldest light, it tells us the universe's age, estimated at 13.8 billion years. Yeah, that number. It's almost impossible to really wrap your head around that time scale. It challenges our whole sense of time, our place in it all. And the sources also point out how astronomy has become more accessible, more democratized. Historically, it was for people with access to huge telescopes, specialized knowledge, right? Observatories on mountaintops. Exactly. But today, amateur astronomy is booming thanks to things like affordable, sophisticated home telescopes, but also smartphone apps. Using augmented reality, your phone becomes a pretty powerful tool for identifying stars, planets, constellations. That's amazing. And historically, the material traces this beautiful intellectual journey from, say, Galileo, using his early basic telescope in the 17th century, which was revolutionary. Then, all the way to the incredible power of Hubble and now James Webb. It really mirrors humanity's persistent drive fueled by technology to understand the cosmos. Building on that observational base, we then get astrobiology, sometimes called exobiology. This is specifically the scientific study of life elsewhere on other planets and other cosmic environments. This field is a true fusion, isn't it? It bridges biology, chemistry, planetary science, astronomy, all focused on pondering the universal origins of life. Yeah, the core question isn't just if life exists elsewhere, but maybe how common it is. Are the processes that sparked life here on Earth common throughout the galaxy, making life likely widespread? Or are we the result of some incredibly rare freak chain of events? And that huge uncertainty, it directly shapes where we look, which missions get prioritized. The sources talk about the search for microbes in specific promising locations. A prime target mentioned is Europa's subsurface ocean, one of Jupiter's moons, under the ice. Exactly. The idea is that tidal forces from Jupiter's immense gravity heat Europa's interior, potentially keeping a vast ocean of liquid water kilometers beneath the icy shell. That could be a habitable environment shielded from the harsh radiation on the surface. Fascinating. And this links to the search for intelligent life, too. Right. Directly. Astrobiology efforts connect straight into projects like the SETI Institute, the search for extraterrestrial intelligence. They use massive radio telescopes to scan huge swaths of the sky, listening for signals. Specifically, signals that look artificial, technological, that wow. Signal everyone hopes for, proving intelligent cosmic neighbors exist. 2. The edge of known reality. Okay, now let's edge into phenomena that often blur the lines between science, fact, unexplained sightings, and maybe popular belief, the unidentified flying object or UFO. Right? The term itself just means an object seen flying that hasn't been identified. But culturally, it's almost always linked to the idea of extraterrestrial spacecraft. And the intrigue around this has shifted recently, hasn't it? It's moved from maybe fringe culture into official government discussion. Our sources mention the Pentagon's recent reports on what they now call UAP's unidentified aerial phenomena. Yes, that shift is significant. These reports have genuinely kicked off serious debate, partly about national security. Some UAPs reportedly show flight characteristics beyond known human tech, and partly, of course, about the highly speculative possibility of alien visitation. So, it's being looked at seriously, but as the deep dive requires, we need balance. Skepticism is important here. Absolutely. The sources are quick to point out that skeptics argue the vast majority of sightings can likely be explained as ordinary things: drones, commercial planes, optical illusions, weather balloons, mundane explanations. Often, yes, yeah, yet that persistent cultural fascination, fueled by movies like Close Encounters, keeps the public deeply engaged with the mystery, with the possibility of the unknown other. Okay, moving from potential visitors to verifiable neighbors. Let's talk exoplanet, defined as any planet outside our own solar system, also called extra solar planets. Discovering these has totally changed our view of the galaxy, completely reshaped it. The sheer number found now suggests planets aren't the exception, they're the rule. Billions, probably trillions, just in our galaxy. A key discovery highlighted in the sources is the TRAPPIST-1 system. Yes, that caused a stir. It did. It has 7 confirmed Earth-sized exoplanets orbiting a small red dwarf star. And crucially, several of them are in the star's habitable zone, the Goldilocks zone. Exactly. The region where temperatures could allow liquid water to exist on the surface. Finding multiple Earth-sized worlds in the habitable zone of one system that radically boosts estimates for potential cosmic habitability. And the methods for finding these distant worlds are incredibly clever. The sources detail the main one, the transit method. Right. Astronomers stare at a star very precisely, measuring its brightness over time. They're looking for tiny periodic dips in the starlight caused by a planet passing in front. Precisely. An orbiting planet crossing in front of its star from our point of view will block a minuscule amount of light. We're talking detecting brightness dips of often less than 1%. It requires incredible precision. And does that method tell us more? It can. If the exoplanet has an atmosphere, some of the starlight will pass through that atmosphere on its way to us during the transit. By analyzing the spectrum of that light, seeing which wavelengths were absorbed, scientists can start to figure out the atmosphere's chemical composition. looking for signs of life, potentially hunting for biosignatures, like oxygen, methane, water vapor, chemicals that in certain combinations might hint at biological processes. Still very challenging, but potential is there. And we owe a lot of this exoplanet boom to missions like Kepler. Yeah, the sources credit the Kepler mission specifically for confirming thousands of exoplanets. During its run, it proved definitively that planetary systems are just incredibly common throughout the Milky Way. Changed everything. 3. The ultimate gravity well. All right, finally in this section, let's confront one of the most bizarre, powerful, and frankly terrifying objects in the cosmos. The black hole, defined as a region in space where gravity is so intense that nothing, not even light, can escape once it crosses a certain boundary. And the journey of black holes, from being purely mathematical quirks in Einstein's theories to things we can actually observe. That's one of the great triumphs of modern astrophysics. The sources rightly celebrate the huge achievement of the Event Horizon Telescope, EHD, capturing that first image, exactly imaging a black hole shadow in 2019. They released that first visual proof. It showed the dark central region, the shadow cast by the event horizon silhouetted against the glowing gas around it. It spectacularly confirmed Einstein's predictions made over a century before. And how did they even do that? You can't see a black hole by definition, right? The EHD wasn't one telescope. It was a global network of radio telescopes, all synchronized, effectively acting like one single dish, the size of the Earth. They weren't imaging the black hole itself, but the absence of light, the shadow it casts on the superheated, intensely bright disk of gas swirling into it. These things aren't just static points either. They're dynamic engines, often at the heart of galaxies. Very dynamic. We now know black holes merge, especially the supermassive ones, at galactic centers. When they spiral together and collide, they unleash incredible energy in the form of gravitational waves, ripples in space-time itself. Yes, ripples traveling outwards at the speed of light, which instruments like LIGO and Virgo here on Earth can now actually detect, opening a whole new way to hear the universe. And this is where reality gets truly weird. Relativistic weirdness. The sources mention time dilation near a black hole. Yes, because gravity in Einstein's view is a warping of space-time. Near a black hole singularity, that warping is so extreme that time itself passes differently. How so? Well, imagine someone falling towards the event horizon. To them, their clock ticks normally, but to an observer watching safely from far away, that falling person's clock would appear to slow down drastically. Seconds for the falling observer could stretch into years, decades, or even longer for the distant one. Mind-bending. Totally. It highlights how gravity fundamentally alters not just space, but time too. Our sources also briefly touch on the information paradox, the deep theoretical puzzle about what actually happens to the information contained in matter that falls into a black hole. Does it vanish forever? That challenges fundamental principles of physics, still unresolved. Okay, we've journeyed from the launch pad's G-forces to the singularity's time warp. Now, let's pull the camera back even further. Look at the biggest picture. The universe's origin. How stars live and die. and the invisible stuff that seems to dominate the cosmos. 1. Theories of origin and structure. We have to start with the standard model, the dominant explanation for cosmic origins, the Big Bang Theory, defined as the theory that the universe began in an incredibly hot dense state and has been expanding and cooling ever since. The core idea is an expansion, not necessarily an explosion into pre-existing space. The theory suggests the initial state was this singularity, or near singularity, which then underwent this period of rapid expansion, inflation, possibly, and subsequent cooling. That primordial expansion sets the stage for everything. And critically, it's not just a neat idea. It's heavily backed by evidence, which is why it's the accepted model. The key piece of observational proof mentioned in our sources is the cosmic microwave background radiation, the CMBB. The CMBB is essentially the afterglow of the Big Bang, the universe's baby. Picture, you could say. It's this faint, almost perfectly uniform glow of microwave radiation filling all of space. Left over from when? From about 380,000 years after the Big Bang. That's when the universe had cooled enough for neutral atoms to form, allowing light to finally travel freely without constantly scattering off charged particles. This faint background hiss is measurable everywhere we look, and his properties match the Big Bang predictions beautifully. And there's other evidence too, right? Yes. The sources note that the Big Bang theory also accurately predicts the observed abundances of the lightest elements, hydrogen, helium, a bit of lithium, that were forged in the first few minutes. This consistency across different lines of evidence is why alternatives like the old steady state models have largely fallen out of favor. The sources also mention the expansion rate, the Hubble constant, and the fact that it's accelerating, right? Measuring how fast galaxies are moving away from us led to the surprising discovery late 90s that the expansion isn't slowing down due to gravity as you might expect. It's actually speeding up. This acceleration is attributed to a mysterious repulsive force or energy permeating space dubbed dark energy, another huge puzzle built on the Big Bang framework. Okay, so from the origin to structure, let's look at groupings of stars. A galactic cluster defined as a relatively young, often irregularly shaped group of stars, maybe up to a few hundred or a thousand, held together loosely by their mutual gravity. These are generally found within a galaxy, not to be confused with clusters of galaxies. They provide really beautiful sights. The sources point to the famous Pleiades cluster in Taurus. Looks like a tiny sparkly diamond cluster in the sky. The Seven Sisters. That's the one. These groupings are bright, often easily recognizable, and tend to be found along the plane of our own Milky Way. And how do they form? They form out of enormous collapsing clouds of gas and dust. You get this burst of star formation where hundreds or thousands of stars are born relatively close together around the same time. They're basically young stellar families, often less than a few 100 million years old, still gravitationally bound before they eventually drift apart over cosmic time. 2. Stellar birth and death. And where does the raw material for these clusters for new stars actually come from? It originates in a nebula, defined as a cloud of gas and dust in space, often glowing, sometimes called interstellar clouds, cosmic fog. Nebula are literally the stellar nurseries of the cosmos. The sources Highlight the famous Orion Nebula as a prime example. You can actually see it with binoculars, this fuzzy patch where new stars are actively being born right now from massive clouds of hydrogen gas. And they're not all the same, are they? The images we see are incredibly complex, breathtakingly complex. Telescopes reveal these intricate structures. You see dark nebula like the famous Horsehead Nebula, which are dense dust clouds silhouetted against brighter backgrounds. They absorb the light behind them. Then you have emission nebula like Orion itself, which glow brightly because the intense ultraviolet light from hot young stars inside them is ionizing the surrounding gas, making it light up like a neon sign. And this highlights the cycle, right? Nebula aren't just where stars are born. Sometimes they're what's left over after a star dies. Exactly. Our sources mention the Crab Nebula. It's glowing intensely, not from new stars being born, but because it's the expanding energized wreckage of a massive star that exploded, a supernova. Which brings us neatly to the dramatic finale for massive stars. The supernova. The colossal explosion of a dying star, briefly outshining its entire host galaxy. This event is absolutely fundamental for cosmic chemistry and therefore for life as we know it. The sources explain the core mechanism. When a star much more massive than our sun runs out of nuclear fuel, its core collapses catastrophically under its own gravity. This iron core collapse triggers a massive rebound shock wave that blows the star apart. And that explosion does something crucial. It's the universe's heavy element factory. That incredibly violent explosion is the only known natural process energetic enough to forge elements heavier than iron. Things like gold, silver, uranium, even a lot of the oxygen and carbon that make up planets and people. They're cooked in the supernova. Cooked in the supernova and then violently ejected, seeded into interstellar space, enriching the gas clouds that will eventually form the next generation of stars and planets, including potentially habitable ones. Have we seen these happen nearby? Relatively nearby, yes. The sources reference supernova in 1987A, which went off in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It was close enough to study in unprecedented detail with modern instruments, giving astronomers invaluable data on how these explosions actually work. And culturally, supernova loom large, don't they? Immensely. They're often depicted as these apocalyptic fireworks, symbols of both ultimate cosmic destruction, but also profound renewal, the necessary death that allows for new creation, new chemistry, new possibilities in the universe. 3. The invisible architect. Okay, we now arrive at perhaps the most mysterious, dominant, and challenging concept in all of modern cosmology. Dark matter defined as invisible matter that doesn't interact with light, doesn't emit it, absorb it, reflect it, but its gravity affects everything we can see. The hidden cosmic scaffolding. We know it must be there because the gravitational evidence is just overwhelming even though we can't see it directly. The classic argument cited in our sources comes from how galaxies rotate. They spin too fast, way too fast. If you calculate the gravity produced by all the visible stars, gas, and dust in a galaxy, it's not nearly enough to hold the outer stars in their orbits at the speeds we observe. They should fly off into space. So something else is providing the gravity. Exactly. Dark matter acts as this Invisible gravitational glue, forming a massive halo around galaxies, providing the extra mass needed to hold them together. It solves these fundamental orbital puzzles, and its dominance is just staggering. The sources emphasize that current estimates suggest dark matter makes up about 85% of all the mass in the universe. Let that sink in. Everything we see, everything made of normal atoms, stars, planets, us, is only about 15% of the universe's total gravitational mass. Dark matter is the silent, invisible majority partner, the architect shaping the large-scale structure of the cosmos, like the web of galaxy clusters and filaments. So, what is it? Are we any closer to knowing? That's the multi-billion-dollar question. Yeah, the hunt is on globally. Since it doesn't interact with light, physicists are trying to detect it through its gravity or possibly through very weak interactions with normal matter. How? They're looking for candidate particles, like WIMP's weakly interacting massive particles. Experiments are set up deep, underground, shielded from cosmic rays, using incredibly sensitive detectors, basically hoping to catch the vanishingly rare ping of a dark matter particle bumping into a normal atom. Still searching. And to help figure out how this invisible stuff behaves on cosmic scales, we turn to cosmological simulation, a branch of computational astrophysics using supercomputers to model huge chunks of the universe's history. These simulations are mind-bogglingly complex, needing some of the most powerful computers on Earth. The sources mention real projects like the illustration. It basically recreates cosmic evolution from the early universe to the present day, showing how structures like galaxies form and evolve within the framework of dark matter and dark energy. So they run the universe in a computer. Essentially. Yes, they can input different assumptions, different properties for dark matter, different amounts of dark energy, and see if the resulting simulated universe matches the large-scale structure we actually observe in the real universe through telescopes. So, they're vital for testing theories. Absolutely crucial, especially for things like dark matter and dark energy that we can't directly experiment on. Simulations let us see how these invisible components would affect the cosmic web, the distribution of galaxy clusters over billions of years. And they can look forward to predict the future. They can extrapolate based on current models and observations. The sources note these simulations help forecast the universe's likely long-term fate, including the rather chilling prospect of its eventual heat death trillions of years from now when star formation ceases, black holes evaporate, and the accelerating expansion pulls everything too far apart for anything interesting to happen ever again. A cold, dark, empty end. #outro. Wow. We have covered an immense amount of ground today. We've journeyed through this intricate lexicon of the cosmos, from the raw engineering and human challenges of getting off Earth, defined by players like NASA, and the physics of acceleration, to the celestial clockwork of eclipses and the dual nature of asteroids as both threat and opportunity. Then we pushed outwards, grappling with the search for life via astrobiology, the mind-bending reality near black holes, and finally zoomed out to the grand cosmic narrative written by the Big Bang theory, shaped by stellar life cycles like supernova and dominated by the unseen influence of dark matter, which we try to grasp using cosmological simulations. It really shows the depth of knowledge embedded in just these 22 terms. Engaging with this vocabulary, you really do get a much richer understanding of modern science, technology, physics, cosmology. Absolutely. It equips you for the conversation. It does. And it raises a fundamental point. I think our whole exploration today highlights how our familiar, everyday concepts like gravity, like time get completely warped, redefined, sometimes even break down at the universe's extremes, near a singularity, or when measuring a whole galaxy held together by something invisible. Right. We struggle to even describe it adequately. We know dark matter dominates, but mostly through its absence of interaction with light. Exactly. Which snorts leads to perhaps a final provocative thought for you to ponder. Okay, let's hear it. Considering that dark matter makes up 85% of the universe's mass, acting as this silent architect we can't see, what else might be out there? What other fundamental forces, or perhaps completely different kinds of mass or energy, might be at play that we haven't even begun to conceptualize yet? Things totally outside our current models. Potentially. What unknown physics might be lurking just beyond the reach of our most advanced simulations, waiting to completely overturn everything we think we know about reality? Something to keep you up at night, or something to keep us curious. Keep asking those huge questions. Keep exploring the vastness of what we don't know. A perfect place to leave it. Until next time on the JBC English Learning Academy.